All right, let's just jump right into it. We've all seen these huge language models do some absolutely mind-blowing things. But there's a ghost in the machine. It's this nagging problem where these incredibly powerful AIs state things with total confidence that are just plain wrong. So how can we actually peek inside the AI's brain and figure out when it's telling the truth versus when it's just making stuff up? That's the mystery we're cracking today.
And this isn't just about an AI messing up a trivia question. Just imagine high-stakes fields like medicine or finance or even law. A confident-sounding but completely wrong answer from an AI could have really serious consequences. This question right here, this is exactly why researchers are working around the clock to solve this.
So, to really get to the bottom of this, we're going to treat it like a detective story. The crime we're investigating, it's called hallucination, and it's the central mystery that really undermines our ability to fully trust these amazing tools. So, what is this crime exactly? Well, officially, an AI hallucination is when a model generates this fluent, totally confident-sounding text that is factually incorrect. But think of it this way. It's not just a simple mistake. It's when the model gives an answer that sounds perfectly plausible, maybe even eloquent, but is completely untethered from reality. It's basically the AI equivalent of a very, very convincing liar. And listen, this isn't some niche little problem. The very people building these incredible systems are the first to admit it's a massive hurdle. This quote, right from the research paper we're looking at, it highlights that solving hallucination is one of the biggest, most persistent challenges in making AI truly reliable. So, how have people tried to solve this crime in the past? Let's call them the old detectives. Now, they had some pretty clever ideas, but as we're about to see, they were missing some really crucial pieces of the puzzle. They were trying to figure out what was happening inside the AI's thinking process. The old methods basically fell into two camps. On one side, you had the black box detectives. They couldn't see inside the AI at all. They could only judge the final answer. Maybe they'd ask the same question a bunch of times to see if the answers were consistent. Then on the other side, you had the white box detectives. They were the ones who could actually get inside the AI's head and look at its internal thoughts as it came up with a response. And this is exactly where those older methods started to fall apart. The black box approach, well, it completely missed the internal reasoning, the how and the why behind the answer. And even the white box methods had their flaws. For example, some of them assumed every single word in a sentence was equally important. I mean, that's like a detective thinking every single piece of evidence at a crime scene is equally critical. It's not how it works. And this brings us to a new detective with a really brilliant insight. The researchers behind this new method, called D2HScore, they realized that hallucinations leave behind a very specific kind of forensic signature. And it's not just one clue, but two distinct, complementary clues that show up inside the AI's process, something they call semantic breadth and semantic depth. Okay, so what in the world are these two clues? Think of it like a really well-written essay. Semantic breadth is like having a rich vocabulary and a wide range of related ideas in your paragraphs. The concepts are diverse, they're well supported. Semantic depth, on the other hand, is like having a strong, consistent argument that develops logically from one paragraph to the next. A truthful AI response, it needs both. A hallucination fails on one or maybe even both of these. So let's look at the first clue, semantic breadth. The whole idea here is that when an AI is generating a factually correct answer, its internal thoughts about the words are really diverse and spread out. But during a hallucination, those thoughts, they collapse. They become super repetitive and narrow, almost like the AI is stuck in some kind of conceptual echo chamber. So how do you actually measure this? It's actually pretty elegant. For each layer inside the AI, you imagine plotting all the word concepts it's thinking about in this virtual space. First, you find the center of that whole cloud of concepts. Second, you calculate the average distance of each concept from that center. A bigger spread means more breadth. And finally, you just average that score across all the AI's layers, and boom, you've got your result. Okay, now for the second clue, semantic depth. This one is all about consistency. As the AI thinks through its many layers, from the shallow ones to the deep ones, its core idea should be getting refined and stronger, right? Not abandoned or randomly changed. A truthful answer shows a clear, logical progression of thought.
And this is super clever. Instead of treating all words equally, which we know is a mistake, this method uses the AI's own attention mechanism to figure out the most important words, the ones carrying the real meaning. Then, it just tracks how that core idea evolves from one layer to the next. A steady, consistent shift suggests the idea is being refined. Small or, totally erratic shifts, that suggests a weak, probably hallucinated line of reasoning.
So we have a theory, we have a method, but does this new detective actually crack the case? It's time to look at the evidence from the experiments and see how this D2H score really performs against the old guard.
And here is our first piece of hard evidence. This chart shows how well it performed on a dataset full of really complex scientific and mathematical reasoning problems. Now, just look at the bar for D2H score. It is significantly higher than the other methods, which means it was way better at telling correct answers from hallucinations in a really tricky subject area. Let's put a concrete number on that success, because the jump is pretty significant. On one particular AI model, the best existing method scored around 41% on this key performance metric. D2H score? It hit 48.42%. That is a major leap forward in detection accuracy. It really proves the method works. And here's the kicker. This isn't just for math problems. The method also nails it on tasks that test broad world knowledge and reading comprehension. As you can see on this chart, D2H score is consistently outperforming, or at the very least, is highly competitive with other methods across all different kinds of tasks. That makes it a seriously versatile tool. And it gets even better. This method isn't just limited to English. When they tested it on math problems in other languages, D2H score successfully spotted hallucinations in both French and Japanese. That proves its core principles are really robust and don't just depend on one language.
So we've seen the method, we've seen the evidence, but what's the bigger picture here? Why does cracking this one case matter so much? Well, because it's a huge step towards building AI that we can actually truly rely on for important real-world stuff.
So let's just sum it all up. The key thing to take away from this whole investigation is that AI hallucinations aren't random. They actually leave behind a detectable forensic signature inside the model. And by measuring those two clues, semantic breadth and semantic depth, we can create a powerful detector that doesn't even need special training. The payoff for this is enormous. Safer, more reliable AI that we can finally start to trust with complex and critical tasks.
And this leaves us with a really fascinating final question to chew on. We've found a way to essentially give an AI a gut feeling for when it might be wrong. So, what do we do with that? The next frontier isn't just about detecting hallucinations after they happen. It's maybe about using this signal in real time to steer the AI back towards the truth, to build models that can actually correct themselves before they ever make a mistake in the first place.